Hello, algebra students. This lesson is called Patterns of Growth. It is the second lesson in our unit on exponential equations. And the goal for this lesson is going to be to compare different patterns of growth. We're really going to focus in this lesson on tables. If you were in class for the first lesson, that was the one about the genie and then choosing between those two options. We had looked a little bit about the math behind the calculations, and we looked at graphs comparing these different patterns of growth. This lesson, like we said, is really going to focus in on what patterns we see when we look at tables representing these different patterns of growth. For our warm-up, to get you prepared to look at a lot of tables today, it's one of these questions which is called Which One Doesn't Belong? There are 3 tables listed there, A, B, and C, and your goal is to pick which table does not belong with the others. Remember, there's no correct answer for this. The focus is really on can you come up with an argument for how that table is different from the others. I encourage you to go ahead, pause the video, look at those 3 tables, see if you notice anything, and see if you can come up with that argument for why your table is different from the other 2. Alrighty, so looking at these 3 tables here, like we said, there is no correct answer for why one of them doesn't belong with the others. The focus is really on can you come up with an argument. For example, some people might say table B doesn't belong with the others because if you look at those x values, and the y values, all of these numbers here, 2, 4, 6, 8, all of these numbers are even numbers, whereas tables A and C have some odd numbers in them. That could be a reason. I did this lesson this morning with my students, and a lot of students picked table C as the table that didn't belong with the others. But the really interesting thing was there's a lot of different ways you can argue why C doesn't belong with the others. So I had a student say, well, C doesn't belong with the other 2 tables because the other 2 tables both have 432 listed in them, but in table C, 4 has a different y value. It's 256. That could be a reason why table C doesn't belong with them. We also had some students actually look at some of the math being done in the tables. So if I'm looking at my first table and trying to figure out how do we go from x to y, you may notice this pattern of multiplying. For example, 2 times 8 gives me 16. 3 times 8 gives me 24. 4 times 8 gives me 32. And when we come to table B, you'll notice that exact same pattern. 2 times 8 gives us 16. 4 times 8 gives us 32. Those also are over here in this first table. But we see that pattern of multiplying by 8. However, when I look at table C, I'm noticing we're not multiplying by 8, and it's also not the same number every single time. For example, up here, there's nothing you can multiply by 0 to get to 1, and then there's different multiplication problems for all of these. So we could say this last table doesn't belong with the others because it's the only table where we're not multiplying x by 8 to get to y. One of the last things I heard this morning was noticing the pattern moving down the table with those y values. For example, if I look at my y column in table A, we can notice a pattern with what's happening to that y value. Take a moment, and if you haven't already, see if you can figure out what math are we doing every single time to get to that next y value. When you identify a pattern, it's going to have a math operation, like add, subtract, multiply, divide, and a number with it. So you may have noticed for this first table, to get to that next value, we're adding 8 each time. 8 plus 8 is 16. 16 plus 8 is 24. 24 plus 8 is 32. Now right here, it looks like that pattern stops, but notice it's just because we jumped a couple more over here. If you filled in the 5, 6, 7 in between these, you would see we're still adding 8 to get us to that 64. For table B, there's a similar pattern. If I look at this table, you may see that pattern also involves addition. 0 plus 16 gets me to 16. 16 plus 16 gets me to 32. 32 plus 16 gets me to 48. And notice that was with us skipping every other x value. If we put in some of those missing ones, it would look like us adding 8, just like we had done over here. But once again, I get to table C and I don't see that addition there. Here we're adding 3, but then here we're adding 12, and this next one's definitely more than 12. So there's not that common addition. There is, however, a pattern. Do you think you can spot it? Remember, if we're looking for a pattern, you're looking for a math operation and a similar number each time. Do you see what that pattern is for table C? It's not addition. This table here has got a pattern with multiplication. Each time I move down those y values, we're multiplying by 4. So we could say table C doesn't belong with the others because it's the only table that's showing that multiplication relationship. Tables A and table B are both using addition to get to the next y value. These are all really great observations for what we're going to be doing in this lesson. We said we're going to be comparing different patterns of growth. And honestly, that's what we were just doing in that warm-up, right? We were comparing these different ways the values grew in the table and these patterns we were identifying from them. I want to quickly plug some math vocabulary into your brain. Like I said, if you were here for yesterday's lesson, it was all about the genie and choosing between those two options. And in that first lesson, we identified 2 different ways that relationships can grow. One of them, we introduced this word linear back in Algebra 1A, but we brought it back in yesterday's lesson. Linear, we said, just meant it was a constant growth. So for the genie one, that was the one where the genie was offering to give you $200 every day. We were adding $200 to that purse every single day. So it meant there was that constant growth or that constant increase. The other word, which was a new word we introduced in yesterday's lesson, was that word exponential. One of the things we had mentioned with that word exponential is it comes from the word exponent. So we had noticed that some of the math we had been doing included an exponent. The exponential relationship with the genie from yesterday was the one where the purse was doubling. We said that word doubling means multiplying by 2, and we were multiplying by 2 again and again and again, which we realized you could just use an exponent to represent. We're going to continue looking at those 2 different patterns of growth. But like we said at the beginning, we're really focusing in on tables and what these relationships look like when you have tables like A, B, and C. So to get us started with that conversation, the first chunk of our lesson is all about growing stores. And when we say growing stores, we mean like a chain of stores that's expanding and growing across the country. So for this first situation, we've got a food company currently has 5 convenience stores, and it is considering 2 plans for expanding its chain of stores. The first plan that we're going to focus in on is Plan A, where that food company opens 20 new stores each year. To help us understand what that means, we're going to go ahead and fill in this table here to get a good picture of what those first 6 years are going to look like. Now notice some of the tables already done for us. We've got this first pair of numbers, year 0 is 5 stores. Year 0 sounds a little weird, but remember that 0 just represents today, right now. So not a year into the future, but the starting point. So they're starting with 5 stores. And we're also told by year 1, there's 25 stores. Where do you think that 25 came from? Well, we're opening 20 new stores each year. So we're adding another 20 here. So the difference between here and here is we added 20. Go ahead, pause the video, and see if you can figure out what the rest of these numbers on our table are going to be. Well, that pattern of opening 20 new stores each year is going to continue. So by year 2, we're adding another 20 stores, which gets us to 45. Year 3, they're going to open another 20 stores. That gets us to 65. And then we've got 85, 105, 125. And we could keep going, right? But our table ends at year 6. There is this last column here about the difference from the previous year. So if I'm comparing that 45 stores to the previous year of 25 stores, what's the difference in those numbers? We've heard difference in terms of subtraction. So you can use that to help you find that difference. Or just like we had done up here, you can think, what would we have to add to get from one to the next? The difference of 45 and 25 is 20. We were adding another 20 stores to get to 45. What about this next one? The difference between 45 and 65 is also 20. We're adding another 20 stores. The difference between 65 and 85, 20. And at this point, my students in my morning class were like, okay, we get it. Each of these are going to be 20. It's that constant adding 20 because the plan is we're going to open 20 stores every year. So that right here is related to our second question. Part A is, what do you notice about the difference from year to year? Well, what do you notice about this number I've been putting in this column? It's the same. We like to use that word constant sometimes. Constant just meaning it's the same each time. We are constantly adding 20 to get to the next year, or the number of stores for the next year. You could say constant, you could say it's the same, the difference is the same from year to year, but we're noticing it's this constant addition in our table. So if I wanted to describe what this pattern looks like mathematically, algebraically, that's related to part B. If there are n stores one year, how many stores will there be a year later? Notice this is not asking us to come up with an equation to represent this, and that might be a little tricky at first. But I'm not saying give me an equation for given what year we're on, what's the total number of stores. I'm just saying if there are n stores. So for example, I say in whatever year there's 300 stores, how many stores will there be a year later? N just represents the stores now, and we're trying to come up with a math expression for how many stores there are 1 year into the future. See if you can figure out what that would look like. Well, this pattern you noticed is going to be super helpful. You notice to get to the next year, we just have to add 20 each time. So if there are n stores this year, then next year I would have n plus 20. To figure out how many stores there are a year later, we're just adding 20 stores to how many stores there are now, or n stores, right? This question here is to really emphasize this addition relationship. Now, someone did also point out if we're going backwards in that table, you can think of it as subtraction. Like we said, the word difference can also mean subtraction. So if you were moving through this table in reverse, we're subtracting. If I had asked this question a little differently, if I asked like how many stores are there the year prior, you could use that subtraction to help you. But here we are expanding, so we're really focusing in on that addition relationship. Now remember the question that said this food company is considering 2 plans. This is one plan where they're adding 20 stores each year. The other plan is this next part. And this plan says that they are going to double the number of stores each year. That word double isn't just like a math class word, but it is really important we know what double means. When you're doubling something, what math does that mean we're doing? So for example, if I had 5 students today and I have double the amount tomorrow, well, if I have double the amount, that's 10. Double, we can think of as multiplying by 2. Lots of times I hear students say the number 2, but specifically we're using multiplication. So that is an important clue to help us with number 1, where we're going to go ahead and complete this table. Just like you did above, I encourage you to pause the video and see if you can fill in these missing numbers. Now, the table we're using here does have an extra column. If you want to go ahead and just focus on these 2 columns here, pause the video and see if, based on this description, you can figure out what those numbers will be and then what the difference is. So we said that word double. If you're doubling the number of stores, means we're multiplying by 2. So once again, our table says year 0, today, we're starting with 5 stores. 1 year goes by. If we double the number of stores, that means the following year, there's going to be 10. 1 more year goes by, we're on to year 2. If I double the number of stores, now there is 20. Notice that pattern is just what we had set up here, is each time we're multiplying by 2. So for year 3, if I double the amount, if I double 20, 20 times 2, 40. Year 4, if I double the amount, 40 times 2, 80. And we can keep doing that multiplication to move us through that table. Someone this morning also had mentioned you can think of double as multiplying by 2, or you can think of it as addition. So to double 5, you can think 5 times 2, or you can think 5 plus 5. To double 10, you can think 10 plus 10. To double 20, you can think 20 plus 20. So if you prefer to think of it with addition, it's the same numbers. Now this other column, the difference between the previous year, we went from 5 to 10 stores. How many more stores did we add? Well, that difference would be 5. We went up 5 stores. Now, if we went from 10 stores to 20 stores, how many more stores did we open? This time we opened 10 more stores. You went from 20 stores to 40 stores. How many more stores is that? What's the difference? 20 stores. And so we can keep going through and finding these differences. Remember, you can always use subtraction to help you with these. So you can think 80 minus 40. That means we went up by 40. 160 minus 80. That means we went up by 80. But we get these numbers here as our differences. Now I want to pause here and talk about 2A. The question is, what do you notice about the difference from year to year? One of the things that stands out to me is how this table looks different than this table up here. Up here, one of the things we had observed about that difference is it's constant. It's the same number. I just kept writing plus 20 again and again and again. That was because with this plan, the plan was to open the same amount of stores every year. The plan was to open 20 stores every year. So the difference was plus 20. Here, though, we see that difference is changing. I can't say we're opening the same amount of stores every year because it changes from year to year. There's some other things you might notice. So I've had some people notice that these numbers are the same. It's kind of just shifted down like that. That's just related to the word double, which is a great observation. I've also had students say that the amount that they're increasing by is twice as much each year. So we might say that. But I think the biggest thing is it's not the same, right? The difference is not the same from year to year. So we could say something like the difference is twice as much each year. Each year that we move into the future, they're adding twice as much as they had the past year. Now, that gets me to this last column here in our table. This last column isn't asking for the difference, it's asking for the factor from the previous year. That word factor we talked about at the very end of last unit, but it might still be like a newer word for you. But factor means we're talking now about multiplication. I'm going to write that word multiplication here. So instead of finding the difference, instead of finding how many stores we added, if I'm looking at the factor, I'm asking myself, how much did we have to multiply by to get from one number to the next? So for example, here it would be asking myself 5 multiplied by what will get me to 10? Well, 5 multiplied by, can I do it? 2 would get me to 10. So that factor there would be we're multiplying by 2. What about to get from 10 to 20? 10 times 2 gets me to 20. What about from 20 to 40? Times 2. And 40 to 80? Times 2. We're noticing here I've got multiplying by 2 as my factor for every single row in this table. So when I get to that question, is there anything you notice about the factor from year to year? The biggest thing I notice is it's the same number. So I could say it's the same factor. There is a constant factor that's multiplied. In this situation, we're multiplying by the same number every time to get to the next row in our table. So one last question here. It's similar to the one for Plan A. If there are n stores one year, how many stores would they be a year later? Just like we did before, see if you can come up with an expression that would describe, if I knew how many stores there are today, what could we do to find the number of stores for next year? Pause the video and try doing part C now. If I started to do it like we did up here, remember up here we were using addition to describe how to get to the next store. The problem is I can't say like, oh, you just have to add this number, because notice every year the amount we're adding is different. That wasn't the pattern. It wasn't constant. What was constant, though, was this doubling, this multiplying by 2. If I knew how many stores there were today, and remember we're calling that n, to know how many stores there are next year, I'm just using this pattern we noticed, and I'm going to multiply it by 2. So you could say n times 2. Now, if you've hung around in an algebra class for a while, you know we don't usually see it written like this. Instead, you might see something like 2n, but it means the same thing. It means we're multiplying 2 by n. And I've also seen students write it with parentheses, you know, all the different ways. But the key there is to describe this pattern, we can't use addition because it's not constant. We would have to, oh my, we would have to use that multiplication. Now at this point in the lesson, I want to pause and just connect it back to what we had talked about in the first lesson in this unit. So that goes back to this idea here. We saw that word double with the genie problem too. Remember, he was doubling the amount of money in that purse every day. And we had seen what type of relationship was that? It was that exponential relationship. So when I think about these two store growth plans, which one of these would represent an exponential situation? That second one, where we're doubling again. I might even write the word in my notes that this is exponential. This is our exponential relationship. So I'm seeing that common factor, that common multiplying by 2 is what would make this an exponential relationship. Now, what about this other one? Is this one exponential? Well, here we're growing by the same amount. So it's that like steady increase. Notice the number of stores here doesn't take off as fast. Whereas here, they're really expanding. They've got a whole bunch more with the second plan. But here, it's just steady growth. Here, every single year, we're just going to add 20 stores. So that wouldn't mean this is exponential. This right here would be our linear relationship. Using that word linear because it's that steady growth or that steady, constant increase of adding 20 each time. That would produce that linear relationship. So to help us with this last part here, this last part is going to give us a little more practice on identifying these different type of relationships. And we're really going to be focusing in on all of the math we've seen so far. So we've seen like different math expressions, and now we've seen some tables, and being able to see which one of these can we use to represent two different situations. So for this last part here, we've got here are verbal descriptions of two situations, followed by tables and expressions that could help answer one of the questions in the situations. So that first situation, number 1, says a person has 80 followers on social media. The number of followers triples each year. How many followers will she have after 4 years? Want to clarify this word triple right here? What's that word triple mean? Triple is like double, but with the number 3. So if today I had 2 students and tomorrow I have triple that amount, means tomorrow I have 6. You're doing 2 in 3 places, or 2 times 3. Situation 2 says a tank contains 80 gallons of water and is getting filled at a rate of 3 gallons per minute. How many gallons of water will be in the tank after 4 minutes? My morning group asked a little bit about that rate and what they're talking about there. The rate is 3 gallons per minute. That just means 3 gallons every minute are being added. You can think of that word rate kind of like speed. It's the speed that this tank is being filled. So we said our goal for this last part here is to practice identifying how we can use math to represent these situations. So there are A, B, C, D, E, and F right here, and we're going to match each of those with one of these situations. The way I would do it in my notes is just say, well, if I think A goes with situation number 1, I could just put A here. If I think B goes with number 2, I could put B here, and so on. This is practice on what this lesson is all about. So please pause the video, try to do this matching, and then come back after you've matched all 6 to see how you did. And go for it. All right. So going through them just one at a time. This first one is saying we're starting with 80, and then I'm multiplying by 3 again and again. We had said earlier that word triple means multiplying by 3. This right here is showing the person starts with 80 followers, and then we're multiplying by 3 each year. We're tripling each year. So as I go through it, here's the starting amount is 80, and then we're multiplying by 3 for the first year, for the second year, for the third year, and the 4th year. Therefore, A would go with situation number 1. When I look at B, this is the focus we said for this lesson is we're introducing some tables now. So the most helpful thing I can do is identify the pattern in this table. If I focus in on those Y values, I'm seeing each time we go to the next Y value, I am multiplying by 3. 80 times 3 is 240. 240 times 3 is 720. And so on. If you didn't know that, first of all, that's fair because there's some big numbers here. But if you're trying to find that multiplication number, you can always use division too. Remember, 240 divided by 3 would give me 80. Or you could do 240 divided by 80 to see that the multiplication number is 3. But again, because it's got multiplication, it's real similar to A. It's just in table form. That means B also goes with situation number 1. When I get down to situation C, C is a little different. It looks like A, but instead of multiplication, we're using addition here. We're starting with 80, and then I'm adding the number 3 4 times. because it's a different math, that's my first clue that it's not situation number 1. But remember, situation number 2 was saying that we are adding 3 gallons each minute. In situation number 2, we're starting with 80 gallons, and then I'm adding 3 for each minute. So there's my first minute, my second minute, my third minute, and my fourth minute. C is going to go with situation number 2 then. We got 3 more. For D, I've got 80 plus 4 times 3. It's similar to A and C because, again, I see that 80 there, but 4 times 3 might be tempting because you see that multiplying by 3. It might be tempting to think situation A, but think about what we said multiplication means. 4 times 3 is just saying I've got 3 in 4 places. 4 times 3 is the same thing as 3 plus 3 plus 3 plus 3. D is another one that's going to go with situation 2. We're starting with the 20 gallons of water, and then we're adding 3 gallons for 4 minutes. That 4 times 3 is just telling me if you add 3 gallons for 4 minutes, you've added a total of 12 gallons. You might also help match D with situation 2 if you actually calculate what all of these are. So 80 plus 3 plus 3 plus 3 plus 3 is 92. So the fact that D also equals 92 is a clue that they should go together. That also could help us with E. When I look at table E, first of all, I see that 92 we're talking about. But we could also match E the same way we matched this first table here, by looking at those patterns. I notice in this table here that each time we're adding 3, so it's related to that situation. It's all about adding 3 gallons per minute. E is also going to go with situation 2. Which just leaves us one last one. F is a little odd. It's 80 times 81, and you might have looked at that first and been like, well, where did 81 come from? But if we look at A or B, it could prove helpful, especially A. Remember, A we said was 80 times 3 times 3 times 3 times 3. We said that went with this first situation. I'm noticing the 80 is the same, but instead of all those multiplying by 3s, I have an 81. Any idea where that 81 came from? Well, if you multiply 3 times 3 times 3 times 3, 3 times 3 I know is 9. I could also multiply these 3's together. 3 times 3 is 9, and 9 times 9 is 81. Both A and F will have the same answer, which is 6,480. F also goes with situation number 1. It's just a different way to write A. Now, speaking of different ways to write A, you could write A as 80 times 81 instead of having all those multiplying by 3s. But with that Gini problem, we saw there's also another way you could write all those multiplying by 3s. If you're multiplying the same number again and again and again and again, how did we say we could represent that? We've said the word in this lesson. If I go all the way back, we could represent it with an exponent. So coming back down, all that scrolling, if I'm looking at this one right here, I could use an exponent to help me. I still need that 80, but instead of saying I'm multiplying 3 again and again and again and again, I could say I'm multiplying 3. How many are there? 1, 2, 3, 4. Multiplying 3 to the 4th power. If you're multiplying the same thing again and again and again, we can make our life easier just by using that exponent. So at this point in this unit, we've done a lot of exploring these different patterns of growth. Really, we've been spending a lot of time comparing and contrasting how linear expressions, linear situations grow, and how exponential relationships grow. So with this extra space here at the bottom, I want to just make this nice little summary table of what we've seen so far. If you think about everything you know, you remember, you've seen these past 2 days about linear relationships and exponential relationships, what are some of the things we've seen? Well, starting with that Gini problem, one of the things we had noticed was the difference in those graphs. Linear equations, if you had me for Algebra 1A, everything we did in the first half of algebra was linear. We're used to linear graphs being these straight lines. With linear equations, linear situations, that straight line could be going up, it could be going down, but remember it was that constant rate of change. Each time with the genie, we were adding $200. Or in today's problem, it was adding 20 stores every single year. With exponential situations, though, we saw yesterday, if you're doubling something or even tripling something like we were in this last problem, you're not going to be increasing the same amounts. For example, here we started off just by increasing by 5 stores, but by the very end of my table, 6 years in, they were adding 160 stores. So we noticed that when we have exponential situations, our graphs look a little different. We noticed in that first lesson, our graphs were these curved lines. That first part of the curve, it starts off a little slow, right, with the penny and the genie, but then by the end, you're increasing a whole lot more. Today's focus, though, was what do these look like when I'm giving you a table? So I'm going to go ahead and put a very rough table in each of these. For linear situations, we noticed that what was that pattern with our y values? Well, I'm looking up here at these two. That pattern was like this, where it's increasing or decreasing by the same amount. So you might be adding the same number each time. It also could be subtracting the same number each time. But there is this common difference. When I say common difference, I just mean like we're adding or subtracting the same amount. So if you think about that table we had filled in where we were adding 20 again and again and again, that's what I mean by common difference. That pattern was we had that same number each time. With exponential situations, though, we noticed that pattern was a little different. With exponential situations, this was where we were multiplying by the same number. So for the doubling one, we were multiplying by 2 each time. Or for the social media one, we were multiplying by 3. For exponential situations, there was a common factor. And by common factor, I mean we multiply by the same amount. So I like this table we did here at the bottom just because I think it summarizes a lot of observations we've made these past 2 days. The newest one being these tables where linear situations are going to have this common difference or like a common number you add or subtract, whereas exponentials we're seeing it's always going to be the same number that's being multiplied. I hope you found this video helpful. Make sure you come to class tomorrow to see our next lesson on exponential growth. It's going to be very exciting. Hope you have a great day. Bye.